All right, so today we're going to be looking at the ideal gas law. So we're not looking at changing pressure, volume, or temp, or anything like that. There's just kind of certain values that are true for gases, and for ideal gases, I should say. We're going to talk about ideal gases in class. But for the most part, the ideal gas law really started off as this relationship between pressure, volume, temperature, and then the number of moles as well. What they found was they were trying to find some ideal, some kind of magic ratio where these things would kind of equal each other. Through some work, they figured out that you need something called a constant. The constant is something we've never used before. It is kind of a number that's always true. It's a universal law in order for certain relationships to make sense. The ideal gas law, they were trying to figure out if you took pressure times volume and divided it by moles temp, what would that equal? And they found out that if you include this constant, PV over nRT, where R is the constant and N is the number of moles, PV over nRT would equal 1 for ideal gases. And so the math was done originally to try to figure out what R is. I would say it's more useful if we take PV equals nRT. It's less math involved. It's just more algebra. It's simpler math. And it allows us to kind of calculate out pressure or volume or the number of moles or the temperature if we're given 3 out of those 4 things. So here's how we're going to make use of this. So looking at that problem down at the bottom there. Calculate the volume. Okay, so right away they're telling us calculate the volume. We're looking for volume. If we're given 3 moles, so in this equation, N is the number of moles, so N equals 3 moles of a gas that will occupy, or the volume will occupy at, okay, so then they give us a temperature, give us a temp of 24 degrees Celsius. Now, for this one, you still can't use Celsius. We're going to want to convert that to Kelvin. So let's just do that right away by adding 273. And I got 297 Kelvin. All right, and the pressure that's at is 1.1 atmosphere. So I probably should have gone through, before I even started, maybe listed out my variables in a specific order, but doing it this way works fine. I just need to go through and plug things in where I need them. All right, so out of my 4 variables that never change, P, V, N, and T, I have 3 of them, so I can calculate the 4th. Starting off with, I've got pressure, which is 1.1 atmosphere, times V, which is what we're looking for, so I leave that V, equals the number of moles, which we said was 3 moles. All right, so R, the constant. Finally getting to talk about it. I forgot to add its units in, which is liters, atmospheres, that's hard to read, per mole Kelvin. All right, it's a crazy unit. Really, it's just meant to cancel out everything else except for one of them. And so we're going to see that here shortly. And it's a really, really small number, but it's what we need to make this work. So it's 0.82057 liters atmospheres per mole Kelvin. All right, and this is taken times temperature, which is 297 K. All right, so right away we can see we have moles here and moles on the bottom here, so that's going to cancel. Kelvin here, Kelvin up top here, Kelvin's canceled. All right, so now I need to get volume by itself. And to do that, I just need to do my algebra right now at 1.1 atmospheres times V. Get V by itself, I just need to do the opposite. And what you do to one side, you have to do to the other. So 1.1 atmospheres, cancel it there. 1.1 atmospheres here. Well, I've got atmospheres on top here, atmospheres on the bottom here, so that cancels. So that tells me the unit I'm left with is liters, and that's good. So looking at this, I've got 3. I can move this over a little bit. All right, so I got 3 times 0.082057. Okay, times 297 divided by 1.1. equals, so that tells me the volume of this gas is 66. And I'm just going to round that to 5 liters, 66.5 liters, okay? That temperature, pretty much room temp. The big thing though is the 3 moles. You know, when we did gas to weight, we kind of knew that at STP, standard temperature pressure, which is 273 Kelvin, 1 atmosphere, 1 mole of a gas has a volume of 22.4 liters. So this makes sense considering we have 3 moles of it, because our pressure really wasn't too much higher and our temp wasn't too much higher. So that answer does make sense. So if I'm working with this many moles of a gas at this temperature and pressure, I would need a container that can hold at least that amount if I need to keep the pressure and temperature there. All right, let's look at one more example problem. Let's just have you guys go right there. Let's go edit clear. All right, so right now we should all have R written down. I will keep that up there. All right, so this question asks, how many moles of gas? All right, so right away they're telling us, actually let's do it this way. All right, pressure, volume, moles. Volume we're gonna list R, 0.0820057 liters atmosphere per mole Kelvin. And T. I'm just going to list them out more. All right. So right away it says how many moles of gas. So it tells me I'm looking for N. Would be present in a gas trapped within a 100 milliliter vessel. So to convert from milliliters to liters, we just got to move our decimal 3 to the left. So 1, 2, 3. So I have a volume of 0.1 liters at 25 degrees Celsius. So to give us Celsius, let's convert that to Kelvin right away. So plus 273, 298. So 1 Kelvin higher. At a pressure of 2.5 atmospheres. So P is 2.5 atmospheres. All right, we're given 3 out of the 4 things we need, or I should say, with the constant, 4 out of the 5. So let's just start plugging things in. So pressure times volume. So 2.5 times 0.1. 2.5 atmospheres times 0.1 liters equals nRT. N's what I'm looking for, so let's leave it in. Times R, 0.0820057 liters atmosphere per Kelvin. And the temperature we calculated out was 298 Kelvin. All right. This time, what I'm looking for is on the right side of the equal side. So what I can cancel out is Kelvin here, cancel that out. Got to get N by itself. Algebra tells me that if we have N times 0.082057 times 298, we just got to do the opposite. I forgot the units here. Liters, atmospheres. That's illegible, but that's okay. Big thing though, that's going to cancel. That cancels. And what you do to one side, we have to do the other. Right? So we've got to have some space here. Let's go parentheses 0. Let's go back and redo that. Alright, so we have 0.082057. Alright. So we have liters atmospheres per mole times 298. Closing parentheses. All right. Liters on top and bottom, so those cancel. Atmospheres, top and bottom, cancel. We're dividing by something that's divided by moles. So the moles are going to end up on top here, and that's good. Moles is what I'm left with. Not that you can read it. All right. So really, the big thing though is my N is equal to 2.5, let's do parentheses, times 0.1 over 0.0820057 times 298. Let's put that in parentheses as well. Let's go to our calculator quick. Clear out what we have there. It's about to get noisy. Parentheses, 2.5 times, where was it? 0.1, closing parentheses, divided by opening parentheses, 0.082057 times 298. Closing parentheses equals, so in this case, the number of moles I have is really, really small. 0.0, that back over. We'll go just 0.01. Not liters, my bad. We didn't find volume. What we found was moles. 1/100th of a mole. Alright, and considering we're using a very, very small volume, that makes a lot of sense. Alright, so with that, good luck on the problems that you'll find on Classroom.